So last lecture we studied Jacobi iterations. We introduced the idea of iterative methods by thinking of a PDE, and instead of solving for the steady state directly, we introduce a time term and time advance all the way to steady state. So Jacobi iteration is pretty much like that, using forward Euler to time advance and using a grid-dependent time step, right? But after we do the derivation of the mathematical formula of doing the Jacobi iteration, we ended up saying that the Jacobi iteration, it's simply splitting the matrix into, basically if we solve AX equal to B, we split the matrix into A, into the diagonal component, let's say D, plus off-diagonal component times X equal to B. And if we don't know exactly what X is to start with, we are just going to split this diagonal component and the off-diagonal component and assign an index k onto the off-diagonal component and index k plus 1 on the diagonal component. Simply doing this, starting from a k0 that is almost arbitrary initial guess. We just keep iterating in the index k, and under certain conditions we can converge in the sense that when x of k is equal to xk plus 1, almost, then we almost solved this equation. So that's Jacobi iteration. And why is it beneficial to do this? It is beneficial to do this. Actually, this formula is practical because inverting D is very easy, right? So if we know x of k, it is very easy to compute xk plus 1. D is a diagonal matrix. Computing the inverse of D simply involves inverting each of these numbers that appears on the diagonal. So the key is that solving D inverse times something is very easy. All right. So that's the motivation of upgrading the Jacobi iteration to Gauss-Seidel. So Gauss-Seidel, it's trying to see, can I split the matrix in a different way so that I have more of the matrix, not just the diagonal, but more of the matrix that is going to be multiplied to xk plus 1, while still making that easy to invert. So what's the idea? Is there any other part of the matrix A that you can add to this part, to the xk plus 1 part, while still making sure it's easy to invert? So last lecture we discussed, right, that a lower diagonal or upper diagonal matrix is very easy to invert. If I have a lower diagonal matrix, I can do forward substitution. I solve the first row first, and then the second row and the third row. Every time for solving every row, I just need to compute one additional unknown. So in Gauss-Seidel, instead of splitting the matrix into D plus OD, I split the matrix into D, the diagonal part, plus a strictly lower diagonal part, which means there is all zeros on the upper diagonal and all zeros on the diagonal. Only non-zeros is on the lower diagonal, plus U, which is strictly upper diagonal. So this split can help us formulate either Jacobi or Gauss-Seidel, right? So in Jacobi, we can just say my OD is actually equal to L plus U. Is equal to L plus U. So that's for Jacobi iteration. And for Gauss-Seidel, we simply say that, okay, instead of just having D, we have D plus L times xk plus 1 plus U, there is only U, xk equal to B. This helps. And as you can see in later in examples, that the convergence rate of Gauss-Seidel is usually faster than the convergence rate of Jacobi. because I have more of the matrix on the implicit part, right? So if I have all the matrix on the implicit part, I converge in one iteration. I basically directly solve the system, but it can be very expensive to do so. If I have only the diagonal part, I have Jacobi. If I have the diagonal plus lower diagonal part, I have Gauss-Seidel. So Gauss-Seidel can be thought of as halfway between Jacobi and just solving directly, which converges in one iteration. Question?
So does it matter if you swap the U and the L?
So does it matter if I swap U and L? Usually it does. We are going to see that basically if you use U instead of L on the implicit part, it corresponds to flipping over all the indices in X and all the indices in B, right? You simply reorder all the grid points backwards. So swapping L and U is equivalent to doing that, and still just apply Gauss-Seidel. And that is one way to reorder in the indices in Gauss-Seidel that makes a difference. There are other ways to reorder the indices in Gauss-Seidel to make even more difference, not just in terms of convergence rate, but also in terms of how you can parallelize the algorithm. We're going to look at it later. So this is Gauss-Seidel. And if you want to analyze the convergence of Gauss-Seidel, you simply do the same thing as we did in Jacobi. We split the matrix, and if we have the exact solution X, we can write it like that. And we define E of K equal to X of K minus the exact solution X, and we get the iteration of the error. So L plus D times E to the K plus U times E to the K, E to the K is equal to 0 because the B subtract out. And we have the iteration to be that. Minus sign, right? So this is now the iteration matrix of Gauss-Seidel. And we're going to look at a little bit later that at what conditions the eigenvalues of this matrix would be all within the unit circle, right? Or the spectral radius of this matrix is less than 1.